In this video, I want to review the scalar product, also known as the dot product, and the vector product, also known as the cross product, and relate them to our unit vectors x hat, y hat, and z hat. All right, here we go, looking at the scalar product first. So, the scalar product of two vectors, a and b, if I have a dot b, that turns out to be the magnitude of vector a multiplied by the magnitude of vector b multiplied by the cosine of the angle between those two vectors if we were to write them tail to tail. Now, we could turn that around. We could look at the scalar product of b and a, that is b dot a, that would be magnitude of the first vector multiplied by magnitude of the second vector multiplied by the cosine of the angle between them. So, a dot b and b dot a are equal to each other. Important thing to note, the dot product, a dot b, and hence b dot a, the result is a scalar, not a vector. And that's why this is called the scalar product. All right, finally, let's take a look at the geometrical interpretation of this. So I've drawn a and b, those vectors tail to tail. Let's drop a perpendicular from the tip of b down to a. We could think of this resulting length as the projection of the vector b onto vector a. Through trigonometry, this length here is going to have a length magnitude of b times the cosine of this angle. So a dot b is just the projection of b onto a multiplied by the magnitude of the vector a. Likewise, we could do the same thing, look at it another way, take the tip of a, drop a perpendicular down to vector b. So this length here will be the projection of a onto b. That length through trigonometry will have length a cosine theta. And so b dot a is just a cosine theta, the projection of a onto b, multiplied by the magnitude of vector b. Again, those give you the same result. So let's look at what this means for our unit vectors. First, x hat dot x hat. Well, the magnitude of x hat is 1. The magnitude of x hat is 1. The cosine of the angle between these two unit vectors in the same direction, well, that's cosine of 0 degrees. There's no angle between them. Cosine of 0 degrees is 1, and we get 1. So x hat dot x hat is 1. For the very same reason, y hat dot y hat is 1, and z hat dot z hat is 1. Now let's take a look at x hat dot y hat. Well, we've got to take the magnitude of the first unit vector, that's 1. The magnitude of the second unit vector, that's 1. And then we've got to take the cosine of the angle between them. But the angle between x hat and y hat is 90 degrees. Cosine of 90 degrees is a big fat 0, so we get 0 for the dot product x hat dot y hat. For the same reason, x hat dot z hat's going to be 0, and y hat dot z hat's going to be 0, and z hat dot y hat's going to be 0, and so on and so forth. All right, so that's how the scalar product plays out for dot products involving x hat, y hat, and z hat. Let's move now to the vector product, also known as the cross product. So here I've got vector A, and I've got vector B, and I want to take A cross B. Well, it turns out the magnitude of A cross B is the magnitude of A multiplied by the magnitude of B multiplied by the sine of the angle between them. And that's the rule for getting the magnitude of the vector. Take the magnitude of the first vector, the magnitude of the second vector, and the sine of the angle between them if you draw them tail to tail. But I want to stress here, this is the magnitude of A cross B. It's not A cross B. A cross B, or any cross product, that is any vector product, gives a result that's a vector. So we also need a direction. Well, to get the direction of A cross B, we stick the fingers of our right hand, put them in the direction of vector A, curl them into the direction of vector B. In this case, we get our thumb in the direction out of the board. That's the direction of the vector A cross B. So A cross B is a vector with this magnitude and this out of the board direction, assuming A and V are these vectors in the plane of the board. Likewise, we could take B cross A, follow the same rule. The magnitude of B cross A we find from first getting the magnitude of vector B, the first vector, put the magnitude of the second vector in there, that's the magnitude of vector A, the sine of the angle between them, if they're drawn tail to tail, and here they are drawn tail to tail, so it's the same angle. So B cross A and A cross B have the same magnitude, but they're not equal. These vectors, these vector products, which are themselves vectors, are not equal. A cross B is not equal to B cross A because it turns out B cross A has a different direction. Let's find it out. Using the right hand rule, we stick the fingers of our right hand in the direction of vector B, curl them into the direction of vector A. Our thumb is pointing in. That gives the direction of the vector formed from the cross product B cross A. That direction is into the board. So A cross B and B cross A have the same magnitudes, but they have opposite directions, hence they're related this way. Finally, again, I want to emphasize that A cross B is not equal to AB sine theta. Please don't ever write this. You might say it's sloppy, but it's not sloppy, it's actually just wrong. A magnitude can't be equal to a vector. All right. Before I move on and look at how this plays out in terms of our unit vectors, x hat, y hat, and z hat, I want to first give a geometrical interpretation of the cross product, which is kind of cool. So let's look at the magnitudes of A cross B or B cross A, since those magnitudes are the same. Let's take a perpendicular and drop a line from tip of B down to A, perpendicular to A. So I'm dropping that perpendicular here. This length will be B sine theta through trigonometry. And so it turns out this, so what we have here is the altitude of a parallelogram. Here's the base of a parallelogram. This product A times B sine theta is the base of the parallelogram multiplied by the altitude of that parallelogram. So the magnitude of a cross product turns out to be the area of a parallelogram formed by putting the two vectors in the cross product together, tail to tail, and then completing sort of a parallelogram there. That's kind of an interesting geometrical interpretation. We won't be using it in this course, but I thought I'd point it out. All right, so now let's move on to a discussion of how this plays out in terms of our unit vectors, x hat, y hat, and z hat. To look at how the cross product plays out for our unit vectors, let's take a look at a right-handed coordinate system. So I've got my x direction to the right, my y direction toward the top of the board, and my z direction will then be out of the board. Into the board would be the negative z direction. Okay, so let's fill in our recipe for the cross product for a couple of these sets of unit vector cross products. So remember, the rule is you got the cross product of two vectors, you get a magnitude, magnitude of the first vector, magnitude of the second vector, sine of the angle between them. That gives the magnitude of this cross product, and then you get the direction by the right-hand rule. For this particular cross product, it happened to be out of the board, but in general, you get it by the right-hand rule. So let's play that out for x hat cross x hat. So here we go. Magnitude of the first vector, well, that's 1. Magnitude of the second vector, that's 1. Sine of the angle between them, well, we have a 0-degree angle between x hat and x hat because they both point in the same direction. So sine of 0 degrees is 0. Well, the directional aspects are irrelevant. We have a magnitude 0. So the cross product, x hat cross x hat, is 0. And that'll be the same for y hat cross y hat and z hat cross z hat. Any vector crossed by itself will be 0. All right, now let's look at x hat cross y hat. Using the same recipe, first looking at the magnitude, I've got the magnitude of the first vector will be 1, magnitude of the second vector in the cross product is 1. I've got a 90-degree angle between x hat and y hat. Sine of 90 degrees is 1, so the magnitude will come out to be 1. So now we get the direction of this cross product by the right-hand rule. Use the right-hand rule, take your right hand, fingers of your right hand go into the direction of the first vector of the cross product, curl them in the direction of the second vector in the cross product, thumb points in the result. So x hat cross y hat is in the direction out of the board. out. So what we have when we take x hat cross y hat is a vector with magnitude 1 and a direction out of the board. Well, that's just the unit vector in the z direction. So x hat cross y hat is z hat. Likewise, y hat cross z hat is equal to x hat. There's a whole bunch of other cross products you can figure out. Remember, if you switch the order of a cross product, you change the sign. So if x hat cross y hat is z hat, then y hat cross x hat would be minus z hat. So when you do all that stuff, you can figure out basically all the different combinations for x hat and y hat and z hat. And that can be very useful because sometimes saying something like out of the board or into the board isn't specific enough. Sometimes you need a three-dimensional specification of your results. Working in terms of your unit vectors allows you to do that. Thank you.